So you got clarity on what we have understood, what we have learned so far, right?
Yes, sir.
Good, Gagan.
Yes, sir.
Give me 1 second. Even though I'm reducing volume, it is not reducing. That's okay. Okay. So we can solve time series problems. The one we solved here, right? The stock market prediction is a time series problem. Okay. There are concepts like seasonality, trend, and stationary time series. So when there is a, let me open that. So when if you look at this graph, right, it is actually going haywire, right, going up and down, like that, because of seasonality and trend, right. It is actually doing, it's actually going like that. But I have taken the original data and tried to implement. But if you can reduce this by doing some pre-processing and then implement a model, right, the model's predictive power will increase. Okay. So to do that, we actually need to understand what is seasonality, what is trend, and how to bring it down, right? How to reduce that seasonality and trend effect. Okay. A repeated pattern within a year is known as seasonality, seasonal variation. Okay. Although the term seasonality means within a fixed period, repeating patterns is called a seasonality. But in time series, in a given year, now summer there will be sales for different kind of clothes, and winter there will be sales for different kinds of clothes, right? So that is kind of seasonality. And trend, sales growth 10% every month is trend, right? How the pattern is changing every month, right? How is the growing or falling effect of some whatever the business scenario we are trying to understand. Seasonality and trend. Okay. In every time series problem, you will have this seasonality and trend. Stationary time series. So we will try to reduce these two before we build a model. So stationary time series means time series are called stationary if they do not have trend and seasonality effect, are reduced, reduced effect of seasonality and trend. Summary statistics, like means and mean and variance, right? Summary statistic means mean and variance are central tendency, and variance will explain how much spread in the data, right? The observations calculated on stationary time series are consistent over time, right? They'll be consistent over time. Now if you take from January to March, and March to June to again October, October to December, four time sequences or time brackets, if you take and try to calculate mean and variance, right, they'll be consistent. Okay. So if for couple of years or within 1 year, it depends on the data. You take 3-4 years of data and you are trying to observe the mean and variance of the data between January and March, first year, second year, third year, fourth year, they'll be consistent. That is called a stationary time series. If we bring data to that kind of a situation, right, the predictivity of data increases. Do you agree? Predictivity of data increases when the mean and variance of the data within a time range comes same, right? Do you agree?
Yes, yes, sir.
Right. First year the mean and variance are 1 and 1.5. Second year also 1 and 1.5. Third year also 1 and 1.5. So we have a pattern there. When you actually build a time series model, it will be able to predict well. So seasonality and trend in general, they will not be like that, right? When seasonality trend effect is there, the data will not be like that. So you need to bring it down to stationary time series. So making a time series data stationary, right? How to make a time series data stationary? Differencing can help stabilize the mean of the time series by removing changes in the level of time series, and so eliminating the trend and seasonality. So what you do is you take consecutive numbers, right? If you take stock price, maybe first day stock price and second day stock price, you take difference. Second day, third day, take difference. Third day, fourth day, take difference. Like that, you take differences and take the differentiated data as your data to build model. Instead of building a model on the original data, you take differences and build a model. So we built a model called as time series has got machine learning models also. Arima and I forgot the names of them. I used only once. So we built a model to predict whether a truck is going to come for maintenance or not. Okay, whether a truck is going to come to maintenance or not in coming, how many days it's going to come to maintenance. So we had data like when a truck went to maintenance. Truck means the lorry, right? So this is for one POC we did for a company, right? When the truck is actually going for maintenance, we had those dates. What we did is we took differences between first maintenance date and second maintenance date and third maintenance date and fourth, like that. There are n number of dates. We got n minus one number of differences, and then we took that data and tried to built the Arima model. It did not work well. We built lean, polynomial regression. It worked well. Okay, when you take those differences, right? Maybe between the first record and second record, second and third, or maybe between first and 10th and 20th and 30th, second and 11th, third and 13th, right? The gap can be anything. Okay, difference in gap can be anything. It depends on the data's pattern. The data's, when you analyze data, right, you will understand how free, uh, how the data distribution is. Depending on data distribution, you need to make that decision of taking the differences. When you take the differences, right, this will actually become stationary. Time series problem will become, time series data will become stationary. So there are different ways of doing it. Lag difference, taking a difference between consecutive observations is called as lag minus 1. The lag difference can be adjusted to suit the specific temporal structure. Temporal structure we call it. So lag minus 1 or lag minus 5 or lag minus 6. It depends how many number of records you are taking differences between, right? Lag difference you call it as. Okay, and differencing order. For some temporal structures, right? For some temporal structures, right? Temporal structures means these kinds of time series structures. We may have to take multiple times differences. You take difference between first one, second one, third one, fourth one, like that, n minus 1 and n. That is one level of difference. And again, after on that differences, right, you will take again differences. First difference minus second difference, second difference minus first difference, third difference minus second difference, fourth difference minus first difference, like that you take. So multiple times you take the difference. You call it as differencing order. Okay, you build a model. After predicting, right, you will get the difference between, if you take differences between first, second, third, fourth, like that, right? You pass third record and predict. It is the difference between fourth and third, right? It is not the original prediction. It is the difference between fourth and third, right? So you need to derive the that day's prediction. Right, you need to, you will have differences of all the records from the day 1 to day n. You are predicting for day n plus 1, right? Day n plus 1. You got the difference between day n plus 1 and day n. You already know day n's value, right? And day n plus 1 value you predicted. So you do whatever is needed to predict the day n plus 1's value, right? I'm actually talking equation here. You understood, right, what I'm saying?
Yes, yes.
Let me take a screenshot. So the same thing we tried to understand when we were actually looking at what you call it as you know heteroscedasticity is there, then you apply transformation on y value, and you build a model, you predict, transformed y will come. You need to apply reverse transformation on y, right? The similar thing we are actually trying to do here. Got it? There is day 1, there is 10, day 2, day 3, right, day 4. We have 4 days of data, 10, 12, maybe 14 and 16. I have taken intentionally. It differences is diff is going to be 2, 2 and 2, right? The model is not needed, right? If the data is like this, right? For day 5 we are predicting, right? We don't know how much it is. So when you build a model, you build a model with these values, right? Differencing order is 1. Only one time you took difference. If you take difference again, right, you'll get 0, 0, 0, whatever, right? So you are using these values and trying to build a model. Now your model predicts, right? Your model will actually give you some number here, maybe 2 or 3. This is actually difference, right? So this is actually the d5 minus d4 is equal to 3, and we know d4 is equal to 16, right? You put d5 minus 16 is equal to 3, d5 is equal to 18, right? That's how you predict. That's how you predict the actual value. Got it? Temporal difference is important. Sorry, differencing order is important. How many times you took differencing order, you need to derive an equation ultimately, and using that equation you will predict the actual value. Got it?
Yes.
If you apply this you know uh, uh, differencing and try to make the data stationary, then you need to do reverse engineering to find out the original value. Okay, the simple concept it is, right? If you are using a deep neural network, this RNN, time series problems can be easily solved. So even when I did not apply the differencing and all that, it was able to predict well. But in diagram, right, it may look like it is working. But if you take the actual differences, right, there is, it predicted the actual value is around 175. The predicted value is around 160. $5 difference. $5 difference means it is not acceptable, right? In a real time scenario, $5 difference in stock market prediction is not acceptable. So if we apply this stationary, if we apply the differencing and make the data stationary, we would have made more progress in making the predictions. So using RNN, you can do very robust time series solutions, but you know we cannot build a very robust NLP modules. NLP modules means first, initially RNN came in to help solve sequence to sequence problems. You give an English sentence, the system should generate a Spanish sentence or Hindi sentence, right? That is actually sequence of words, because when you look at two different languages, right, word to word mapping will not be there. There will be combination of words which will be affecting combination of words in the target time series, right? So target series. So it is a sequence to sequence problem. Input is one sequence, output is another sequence. The output sequence is dependent on input sequence. So I tried to build that model. It's a old code. It may not work now, and we have a new class called sequence to sequence in TensorFlow to 2.4. Using that, right, it'll be easier to build a what you call it as the sequence to sequence model. Give me one sec. Oh my goodness. I don't know whether I have it here or not. Let me show you that sequence to sequence. That file will not work, but now I built it long back. No. Let me go back and try to find it. So I need to rewrite this code. That's where I didn't pull it into the new course content. This is stock market prediction. Yeah. Text summarization. Language translation. This is the one. No, not this one. So, at least theoretically, you should understand what exactly it is so that you can do experimentation. Okay, I am missing. Oh, that file is missing, but let me show you. See, this is the diagram, right? So there will be an encoder, there will be a decoder, right? Encoder will have multiple. How are you is input. I am good is output. So you have data like this, right? There is a input data, there is output data. You are passing input data and trying to generate output data. How are you doing that? You are passing first, this vector for how into the first cell, RNN cell, and hidden state will be fed to the next one. R, U, like that, The last node's outcome is going to be passed as input for the first node, but there is no, here we have some input here, right? But for the decoder, there is no input. So we'll take some dummy input while training, say go, okay? And then we pass the I am fine sentence. So whatever it is generated, it is going to keep compared with I, and that generated value is going to be passed as input to the next layer, next cell. And yam, it's going to be compared with I am. This is y. There will be y cap generated. That y cap is going to be sent, right, as hidden state, and this I is going to be sent as input while training, right, while training. Okay, and yam is going to be sent as input, and hidden state is going to be sent, whatever generated value is going to be sent as hidden state to the next layer. But while prediction in production, right, we will not have these values. Whatever first cell is predicted is going to be fed as the input for the second cell. Whatever second cell predicted is going to be fed as the input for the third cell, like that. Got it? Basic idea of a sequence to sequence model, language translation model. Any questions? While training, you will have the y values, the decoder sequence, right? Sorry, input and output both will be there. So you will feed the output values, output words as input to the RNN cells. But in production, you will not have these values. So whatever is predicted is going to be passed as input. Got it, Cecil?
Yes, sir.
So this can be built easily now. Sequence to sequence. TensorFlow. There are previously we had to write lots of code to build it, right? And the fact is, um, PyTorch is easy to do than TensorFlow, and faster also. And most recently, we found that, basically we were very excited about TensorFlow and started building code and all that. But now our production code is all in PyTorch. Okay. So you can look at it and you will understand there is not going to be much there. This particular concept is implemented there. Okay. So you start doing it. If you have questions, I'll explain. Okay. So on a sequence to sequence model, RNN will not work well. Initially, RNN started promising that RNN will work well on sequence to sequence models. Even we tried that, tried building that kind of a model for a month. Okay, for Tata Power, we did a POC 2 years back, and we tried to build an RNN model which actually tries to generate email response. It takes email. Uh, there were around 42,000 emails, received emails and responded emails. We tried to take that data and build a sequence to sequence model and then tried to run it. We were actually training that for 10 days long, 1 week, 10 days long, but still it did not work well. It used to generate some junk text. Okay, even there is another concept called bi-directional RNA. Okay, bi-directional RNA. So, this can be used for sequence to sequence generation or image text classification also, because um, when you look at a sentence, um, so yeah, so uh, so Johnny, the president, promised to deliver something. Okay, Johnny, the president, promised to deliver something. Johnny, the president, actually says that Johnny is a person and he is a president of a country. Okay, okay. Johnny, the dog, is playing well with my kids, right? Johnny, the dog, is actually saying that Johnny is a dog, right? The name is same, but one place it is it's a president, and another place it is a dog. So you need to look into if you look in one direction only, right? What is this unidirectional RNA is doing? It is looking in one direction only, right? Like that, it is going forward only. If you don't look backward, Johnny in both places will be considered the same, right? And model may get confused and it may not produce good results. If you look at the forward direction and backward direction both, then you understand that this Johnny and that Johnny are different. One Johnny is president and another Johnny is dog, right? That is called as bidirectional RNA. So how will it work? You pass time step to every LSTM cell, or whatever cell, right? Only relu sorry tanh cell also, but tanh cell will not work that efficiently because it will not remember many things by the time it reaches the end. Okay, so if you take LSTM cells, you pass XT to forward forward network and backward network both, right? The understanding will be the hidden state will be passed to forward, hidden state forward, backward direction also, hidden state to the backward. So two networks working, one in the forward direction, another in the backward direction. It is like reading the text from left to right and right to left, and combine both and try to produce something. This combination can be a sum, a multiplication, or average, or an activation function. It depends. Whichever works, we will do that. Okay. Sometimes what you do is you do forward backward the bidirectional RNN, but you take output from only the first layer or the first node or the last node, because when it is doing bidirectional, right, many iterations it is doing, so it will have some understanding here. Okay, so next iteration the weights will get adjusted, next iteration weights get adjusted. So these this backward direction y cap will also have some intelligence. You are combining them and trying to predict. So if the data is like that, you need to look in the forward and backward both directions, then you should be building a bidirectional RNA. So this is also not that difficult. We have classes to do. See, bidirectional is the class. Layers bidirectional. And then you specify, no, merge mode is concatenate, right? What is this merge mode? This last, this thing. Merge mode, do you want to do some merge? Concatenate means the outcome vector here and outcome vector here will be concatenated and created. 3, 3, you will get 6 dimensional vector there. Okay. And then layers, you specify layers, it will actually automatically create the structure. See this? Add LSTM and LSTM. So in each, in the forward direction and backward direction, you have 2 layers. I am showing 1 layer here, right? 2 LSTMs here, okay, in that example. And then last layer dense, last layer on the end layer. Here they used a dense layer. Okay, after the outcome merged, they took a dense layer. Okay, and categorical cross entropy, the activation function, the dense and activation, right? This is all same, right? Forward, the backward layer, and bidirectional, it is taking forward and backward with custom backward layers. Give me 1 second. I think 2 examples they merged here. Give me 1 second. Yeah, 2 examples. In this way also we can do. We take model and then take forward, take backward, and go backward true, and then bidirectional forward and backward, right? Dense activation. This is another way of doing it. So this became very simple. When I tried to write this 3 years back, right, I had to write like around 100 lines of code. Okay, got it? Theory you got it, right? How is it working? Where it will help? Shishram.
Yes, yes.
So that's it, I would say. With that, right, we can say our course is kind of ended on a note that we have to do more research, right? We have to do more research. We have to work a little more harder, and you need to spend time, right? So,
Yeah.
any questions